7.2 Reflections and Rotations. Now, any linear transformation can be defined by the effect it has on the unit vectors 1, 0 and 0, 1. And the reason we choose these particular unit vectors is because they're the easiest numbers to work with. So we consider the effect of a transformation on the coordinate 1, 0 and also on the coordinate 0, 1. So with that, the transformation represented by the matrix M, where M has elements A, B, C, D, will map 1, 0 to AC and 0, 1 to BD. Now let's actually take a look at this. If we have the point 1, 0, and if we transform this point over here using this matrix, so we pre-multiply the vector 1, 0 by this matrix, so here we've got A, B, C, D. If we multiply all of this out, you can see here we've got A times by 1, that's A, plus B times by 0, that's 0, and then here we've got C times by 1, that's C, plus D times by 0, so on the bottom we get C. And if we consider this coordinate of 0, 1, we can pre-multiply this vector by this matrix again, and let's see what we get. So if we pre-multiply by A, B, C, D, and if we multiply these out, A times by 0, that's 0, and B times by 1, that's B, and then C times by 0, that's 0, D times by 1, that's D. So clearly, you can see this matrix will map 1, 0 to AC, as we've shown here, and this matrix will map 0, 1 to the matrix BD, as shown over here. So what we have over here, these images will be the columns of our transformation matrix. So what does that mean? Our transformation matrix when we come to work out the transformation matrix, for the first column we have AC, for the second column we have BD. So this is the transformation matrix which we're looking at. You can visualize this transformation by considering the unit square. So we've got the unit square over here, S. Now, the linear transformation -2, -1, -1, -2, this stretches and rotates the unit square S to produce the image S dash. Now, how do we know that? Well, we'll take a look at how we know that in a later video, but for now let's consider what we mentioned here by applying this transformation to these coordinates over here. So if we consider the origin has coordinates 0, 0 obviously, and we will apply the transformation matrix to the origin, so we will apply this matrix to these coordinates, so we will apply -2, -1, -1, -2 to these coordinates here. So if we work this out, well, here we've got 0 plus 0 on the top, and on the bottom we've got 0 plus 0. So when we have our point being the origin, when we apply a linear transformation to that, you can see the origin does not change on under a linear transformation. Now let's consider this point over here. Let's consider the point 1 across 0 up. So to find out where the new image, rather the new point, will lie, we will apply the matrix transformation to this point. So we will apply -2, -1, -1, -2 to this point here. So if we work this out, well, here we've got -2 plus 0, and here we've got -1 plus 0. So you can see here, when we transform 1, 0 by this matrix, we end up with, as you can see over here, -2, -1, which is over here. So this point has moved to this point over here. Now if we consider the point 0, 1, which is this point over here, again, to find out where this new point will be after the transformation, we need to apply the transformation matrix to this point. So we will apply -2, -1, -1, -2 to this point. So working this out, we have 0 plus -1, and then we've got 0 plus -2. So we've got -1, -2, that's here. So this point over here moves to this point. And if we now consider the point 1, 1, let's find out where this point will move after the transformation over here. So we will multiply this vector by -2, -1, -1, -2. So if we work this out, we have -2, -1, that's -3, -1, minus, and then on the bottom we've got -1, -2, that's -3. So this point over here has moved to this point over here. Now, this all makes complete sense. If you think about it, let's suppose over here we want to actually find out what linear transformation matrix we have. Let's suppose we want to go from, say, 1, 0 to the point -2, -1. And also we want to go from 0, 1 to -1, -2. We're figuring out what matrix do we need to get these results over here. And if we get this, then of course everything we've said makes complete sense. So if we have A, B, C, D multiplied by 1, 0, well, if we multiply this out, we've got A plus 0, so that's just A. Here we've got C plus 0, so that's just C. And here we've got A, B, C, D multiplied by 0, 1. So if we work this out, we're going to have 0 plus B and C plus 0 plus D. So these over here will represent the columns of the linear transformation matrix. And of course, if we match what we have over here with what we have over here, then you can clearly see we've got A, which is -2, C, which is -1, and for our second column, we've got B, which is -1, and D, which is -2. So this is the transformation matrix. Okay? If you've got a transformation of the vectors A plus B, the special thing about linear transformations is this property over here. The transformation of A plus B, that's equal to transformation of A plus transformation of B. So you can add the two image vectors to find the fourth vertex in this shape. So we're adding this image vector to this image vector to get this image over here. This means that the entire transformation can be defined by the images of the two unit vectors 1, 0 and 0, 1. So that's why we consider these unit vectors when we consider the effect of a linear transformation. Okay? And there's two other important points which we need to know. Points that do not move under the given transformation are called invariant points, and lines which do not move are called invariant lines. So you can see here the origin is an invariant point. And that's what's mentioned here. The only invariant point in this transformation is the origin, which is always an invariant point of any linear transformation. Example number 4. The transformation U, represented by the 2×2 matrix Q, is a reflection in the y-axis, and we have to write down the matrix Q. So to approach this question, for part A, we can first of all draw on a quick set of axes as shown over here. So we've got the x axis and here we've got the y axis, and let's just extend this line down a little, and here we've got the origin. Now if we have the unit vector going across as shown over here, if we go across by say 1 unit, we've got coordinates 1, 0, and if we go up 1 as well for the unit vector in the y direction, here we've got coordinates 0, 1. Well, if we reflect in the y-axis, hopefully here you can see this point goes over here. So if we reflect this point will go to this point over here, and if we reflect in the y-axis, this coordinate will be -1, 0. So what you can see over here is this 1, 0, this will map onto -1, 0, this 0, 1, this will map onto 0, 1, it's not changing, and therefore the transformation matrix Q, that's equal to -1, 0, 0, 1. This matrix represents a reflection in the y-axis. Now for part B, we have to write down the equation of the invariant line of this transformation. Well, if we recall, an invariant line are basically lines which map onto themselves. So you can see here, the lines which map onto themselves, that will be x equals 0, y equals 0, and y equals 1. So for part B, we have x equals 0, y equals 0, and y equals 1 as the invariant lines. So each point on the mirror line, the y-axis, is invariant. So this line over here is invariant. That's basically x equals 0. And any line perpendicular to the mirror line will also be an invariant line. So what's perpendicular to this? We've got over here this line, which is perpendicular, and this line, which is perpendicular. Okay? So any line perpendicular to the mirror line will also be an invariant line, although the points on the line will not, in general, be invariant points. Let's suppose we have a coordinate axis. Something looking like this. Now, as usual, like we've been saying all this time, we need to consider the unit vectors 1, 0 and 0, 1. So if we show the unit vector 1, 0, that's over here in red, that has coordinates 1, 0. And if we show the unit vector 0, 1, in terms of coordinates, of course, that will be 0, 1. Now, if we were to reflect in the y-axis, you can see this point won't change, but this point over here, the 1, 0, that will be reflected to this point over here. So the coordinates of this will be -1, 0. So what you can see over here is this coordinate of 1, 0, this is being mapped to this coordinate here of -1, 0. What you can also see is that this coordinate here, the 0, 1, that's being mapped to itself. So it's being mapped to 0, 1. So how does this help us? From this we can form a transformation matrix. If we do that, we've got the components here, -1, 0, and the component here for this column, 0, 1, and what all this is representing is a reflection in the y-axis. So this matrix represents a reflection in the y-axis. Now, the points on the y-axis are invariant points, and the lines x equals 0, that's this line over here. Sorry, the line x equals 0, yeah, that's this line over here, and the line y equals k. Those are what we call invariant lines. In other words, they don't change, and you can see that over here. So in this case, y equals 1 is an invariant line. You can imagine that over here. Let's now imagine another coordinate axis. Something looking like this. Now, again, as usual, we begin with the unit vectors 1, 0, and also 0, 1. So let's just show 0, 1. Here is 0, 1. Now, if we were to reflect in the x-axis this time, you can see that this point isn't changing, but this point over here, the 0, 1, that will move to this point over here. So let's just show that. We've got here 0, -1. So how does that help us? Well, what you can see over here is that the 1, 0 that's being mapped onto itself, as we see here, but this point over here, the 0, 1, this point over here is being mapped to this point over here, 0, -1. So how does this help us? Well, from this we can form a matrix. Well, here for the first column we've got 1, 0. For the second column we have 0, -1. So this over here will represent a reflection in the x-axis. So we have a reflection in the x-axis represented by this transformation matrix. So the points on the x-axis are invariant points, so that's everything on this axis, and the lines y equals 0 and the lines x equals k, so x equals k over here. Those are invariant lines. Now, in the notes, you need to basically memorize this matrix over here is a reflection in the y-axis, and this matrix over here is a reflection in the x-axis. And if you can't memorize that, then think about the mapping of points, which will help you visualize what's going on, as we have just shown here. Example number 5, we've got this matrix P over here with elements 0, -1, -1, 0, and we have to describe fully the single geometric transformation U represented by the matrix P. Well, for part A, the way we can approach this question is to think about our unit vectors. We've got our unit vector 1, 0, and if we take a look at this first row, this first column over here, you can hopefully see this is being mapped onto 0, -1. And what else you can hopefully see, if we consider the unit vector in the y direction, 0, 1, hopefully here you can see this is being mapped onto the image -1, 0. So knowing this and this will tell us this transformation matrix here. So our next step is to show all these lines on a diagram, and from there we can figure out which transformation we have. So if we consider this unit vector 1 across 0 up, let's just show that over here, and let's add in the coordinates 1, 0. This is moved to this unit vector, but in the negative y direction. So we have 0 across, 1 down, and we see that over here. So we have here 0, -1. And if we consider this unit vector in the y direction, 0 across, 1 up. So here we have 0, 1. This has moved to -1, 0. So -1, 0, that's over here. So knowing this, you can hopefully see here, this point has moved to this point has moved to this point, and therefore, hopefully here you can see we have a reflection in this line over here. And this line over here is the line y equals minus x. So what we can therefore conclude is the following. The transformation U represented by the matrix P is a reflection in the line y equals minus x. So what does this mean? Well, we've got this matrix here with components 0, minus 1 for this column, and minus 1, 0 for the other column. This is a reflection in the line y equals minus x. Now for part B, given that U maps the point with coordinates AB onto the point with coordinates 3 plus 2A, B plus 1, we have to find the values of A and B. So for part B of the question, we've got our point A, B, and this is being mapped onto the point 3 plus 2A and B plus 1. So to go from here to here, we need a matrix that multiplies by this vector to give this vector here. And that matrix we're going to be multiplying by is, of course, matrix P, because U maps this point onto this point. So matrix P, that's 0, minus 1, minus 1, 0. So how does this help us? Well, if we expand out, for the top row here, we've got 0A minus B. So we've got minus B, and this is equal to 3 plus 2A, and here we've got minus A plus 0B, so minus A plus 0B, this is equal to B plus 1. We have to solve these two equations simultaneously. So if we rearrange from here, you can see that we have 2A plus B equals minus 3, and here you can see we have A plus B equals minus 1, and if we subtract the equations, we can therefore conclude A is equal to minus 2, and when A is equal to minus 2, B is equal to 1. So that's the value of A and B. Now let's draw on a coordinate axis. So something looking like this. We've got X over here and we've got Y over here. As usual, we begin with our unit vectors. So we've got 1 across in the X direction, so here we've got 1, 0, and we've got 1 unit up in the Y direction. So here we've got 0 across, 1 up. Now our goal over here is to reflect in the line y equals x. Now the line y equals x, that's shown over here, y equals x. Okay? Now if we were to reflect this point in the line y equals x, so this point here, it will go over here to the point 0, 1. And if we reflect this point in the line y equals x, this will go to this point over here. So this will go to 1, 0. Okay? So if we think about our mapping, if we go from the red to the orange, we're going from 1, 0, okay, to the point 0, 1, okay? And if we consider this blue one over here, the 0, 1, if we consider our mapping, this goes to this point in green over here, the 1, 0. So how does this help us? From this we can form a matrix. For the first column, we've got the 0, 1. For the next column, we have a 1, 0. And this over here will represent, therefore, a reflection in the line y equals x. So that's what we see over here. You can see here that the points on the line y equals x will be invariant points, and the lines y equals x and the lines y equals minus x plus k are invariant lines for any value of k. Now again, let's draw a coordinate axis. So if we do that, we have the following. So let's just show this over here. We have y and x, and as usual we will begin with the unit vectors. We have 1 across here, so the coordinates here are 1, 0, and we have 1 unit up here. Okay, so here we've got the coordinates 0, 1. Now let's suppose we want to reflect in the line y equals minus x. What would this look like? Well, first of all, let's just draw the line y equals minus x. So here we've got the line y equals minus x. Okay? So if we were to reflect these points in the line y equals x, hopefully here you can see this point over here, the point 1, 0, that goes to the point over here with coordinates 0 across, 1 down. So this goes to this, and if we consider this 0, 1, if we reflect that in the line y equals minus x, this goes to the over here. So here we have what we have over here is minus 1, 0. Now if we consider our mappings, we begin with the 1 across 0 up, and this over here is being mapped onto this point over here, the 0, minus 1. And if we consider this point here in terms of our mapping, you can see here this point goes to this point, the minus 1, 0. How does this help us? Well, here we can form a matrix. The first column of this matrix will have elements of 0, minus 1, and here we have minus 1, 0. So what does this represent? Well, this over here would represent a reflection in the line y equals minus x. Okay? So what we see over here is that the points on the line y equals minus x, so every point on this line are invariant points, they don't change, and the lines y equals minus x and y equals x plus k for any value of k are invariant lines. Okay? So if you take a look in the notes, you can see over here, this matrix will represent a reflection in the line y equals x. This matrix here will represent a reflection in the line y equals minus x. And over here, we showed how to derive those transformation matrices. Let's now draw another coordinate axis. Something looking like this. Okay, so we've got the y over here and we've got the x over here. And as usual, we will begin with the unit vectors. We've got over here 1 unit across, 0 up, and here we've got 0 units across, 1 unit up. Now let's suppose we want to rotate by 90 degrees anti-clockwise. Now it's important that you note we have an anti-clockwise direction. That's super important. If we were to rotate 90 degrees anti-clockwise is going this way, so this point over here is moved to this point over here. So this point goes to the point 0, 1. And this point shown in blue, if we rotate 90 degrees anti-clockwise, you can see this point will go over here. So this point will go to the point -1, 0. So if we consider our mappings, we first of all can consider this 1, 0, and in terms of the mapping, we're going to 0, 1. Okay, and if we consider this point over here, the 0, 1, after our mapping, we're going to this point over here shown in green, -1, 0. So if we were to form a matrix from this, we have 0, 1, then -1, 0 as this transformation matrix. So this transformation matrix over here, we have a rotation 90 degrees anti-clockwise about the origin. Let's draw on another set of coordinate axes, okay? So something looking like this. We've got the x over here and the y over here. Now, as usual, we begin with the unit vectors. We have 1 across, 0 up here, and we've got here 0 across, 1 up. Okay, so what we can now do is Well, let's suppose we want to rotate by 180 degrees. Okay, if we were to rotate by 180 degrees, you can see this point over here will go to this point over here. So let's just show this point. So rotating this point by 180 degrees will go over here. So this point is -1, 0. And if we rotate this point 180 degrees, you can see this point will go to this point over here. So coordinates of this is 0 across, 1 down. So if we consider our mapping, we begin with the 1, 0, and this over here is being mapped onto the -1, 0. And if we consider this point 0, 1, this is being mapped onto this point shown in green over here, 0, -1. So if we form a matrix from this, we have -1, 0 for this column, and we have 0, -1 for this column. So what will this represent? We would have a rotation of 180 degrees about the origin. So we have a rotation 180 degrees about the origin. Let us once again draw a coordinate axis. Something looking like this. Okay, we've got the y over here and we've got the x over here. Now the first thing we need to do, as usual, is draw on the unit vectors. So we've got the unit vector over here, 1 across, 0 up. We've got the other unit vector going up, zero across, 1 up. Now if we were to rotate by 270 degrees anti-clockwise, well, rotating this point 90 degrees will go to here, 180 degrees here, 270 degrees, that'll go here at the 6 o'clock position. So this point here is 0, -1, okay? And if we consider this point over here, if we rotate this by 270 degrees, well, we've got 90, 180, 270, so if I rotate this by 270 degrees, we'll end up at this point over here with coordinates 1, 0. So if we consider our mapping, we start off with the 1, 0. You can see here the 1, 0 ended up at 0, -1. And if we consider the 0, 1, you can see that ended up over here at 1, 0. Okay. So in terms of our matrix, we have here for the first column 0, -1, and for the second column we have here 1, 0. So you can see here that we have this matrix which represents a rotation 270 degrees anti-clockwise about the origin. So it might be worth memorizing these various matrices, but if you can't memorize them, you can always derive them, as we've shown here. Example number 6 the transformation U, represented by the 2x2 matrix P, is a rotation of 180 degrees about the point 0, 0. And for part A, we have to write down the matrix P. Now, as we've just discussed over here, if we have a rotation of 180 degrees about the origin, we end up with this vector over here. And of course, you can derive this as we just discussed. So, the matrix P, that's equal to -1, 0, 0, -1. And you can see the added benefit of actually memorizing these matrices instead of deriving them, because it will save you a lot of time in the exam. Now for part B, we have to write down the coordinates of the invariant point of this transformation. So to do this question, for part B, if we take a look at what we have over here, we're looking for the invariant point, the point which doesn't change. And you can see over here, the only invariant point will be the origin. That doesn't change. So therefore the coordinate of the invariant point of this transformation will be 0, 0. Let us now draw another set of coordinate axes. Something looking like this. Now, as usual, we will consider our unit vectors. So, first of all, we've got the unit vector along the x-axis. So this will have coordinates 1, 0. We've met that before. And if we think about what's going on in the y direction, well, here you can see we have 0 across, 1 up. Now let's suppose we are rotating anti-clockwise by, say, an angle theta this time. So before we rotated by nice angles, 90 degrees, 180, 270, etc. But let's suppose we want to rotate by, say, an angle of theta from the x-axis in an anti-clockwise direction. What would we do in that situation? Well, first of all, let's draw everything. So, if we rotate by an angle theta anti-clockwise, then this point will go over here somewhere. Okay, and we'll deal with the coordinates of that later, and you can see that this point will be also rotated by the same angle. So here we end up with this situation. Okay, so what have we done over here? Well, clearly you can see we've rotated by an angle of theta here, and this point over here has also been rotated by an angle theta in an anti-clockwise direction to get this point over here. Okay, so how does this help us? Well, essentially we want to figure out what the coordinates of this point is and this point is over here. And to do this, we need to consider essentially trigonometry. So perhaps if we form a right-angled triangle from this point here, and you've already met stuff like this when we did complex numbers. Of course, if we say that we have a unit length of 1 over here, so let's just, because here we've got a, let's just do it in a different colour actually. if going across we've got a length of 1, when we rotate that, this will still have a length of 1. So this side over here will be 1 times by the cosine of theta, so that's just cos theta, and this over here is 1 times by the sine of theta. So how does this help us? From this we can find out what the coordinates of this point is. Of course, here we have cos theta, sine theta. Okay, and if we do a similar thing for the one shown in green, then again, if we form a right angle triangle from this, as shown here, and also this, well, this length over here, because this one in blue has length 1, if we rotate it, this length will be 1. And this length over here will be cos theta. Okay. And this over here will be sine theta. So how does that help us? Well, if we find the coordinates of this point, well, it'll be, as we can see here, in the y direction it's cos theta. Now in the x direction it's going the opposite way to the positive x-axis, so here we'd have minus sine theta as this coordinate here. So how does this help us? Well, if we think about our mapping, you can see here that this point 1, 0, this point here has been mapped onto this point over here. Okay, this point has been mapped onto this point, cos theta, sine theta, and this point of 0, 1, well, what you can see here is this point has been mapped onto this point which we showed in green, which is minus sine theta cos theta. So in terms of our transformation matrix, if we form our transformation matrix for our components, here we have cos theta, sine theta, and then for this column we have minus sine theta cos theta. Okay, so what does this represent? What you can see here is we have a rotation of an angle theta anti-clockwise about the origin. So if you take a look in your notes over here, that's exactly what's mentioned. Now, happily for us, in the formula book on page number 17, this is given. An anti-clockwise rotation through theta about the origin, that's given by this transformation matrix, cos theta minus sine theta, cos theta. Now, just as a extra detail, if theta is equal to 180 degrees, any line passing through the origin is an invariant line. So please do bear this in mind. Now, of course, the only invariant point when we rotate by an angle theta anti-clockwise about the origin is the origin. Let's draw a set of coordinate axes. Let's suppose something looking like this. Now, let's suppose we've got our typical unit vectors. So here we've got 1, 0 in this direction, and here we've got 0, 1. Now what would happen if we suppose reflect in, say, this line over here? So let's just quickly draw that on. Suppose something like this line. So we want to essentially reflect this line and, sorry, this point and this point about this line over here. Now what's the equation of this line? Well, clearly it's going to be y equals something, lots of x. It passes through the origin. Now the gradient of this line, if we think about forming a right angled triangle, here we have the, well, first of all, let's suppose that the angle that the x-axis makes with this line here is theta. Okay, so let's suppose we've got theta degrees here. If we form a right angled triangle, something looking like that, here we've got sine theta, here we've got cos theta, so the gradient is changing y over changing x, sine over cos, that's equal to tan. So the gradient of this line is tan theta. And then of course we multiply by x. It's a straight line, it's in the form y equals mx plus c. C is equal to 0 because it passes through the origin. Now figuring out where this point ends up if we reflect about this straight line, well, it might help if we rotate our paper to form a vertical line. So this point will go over here somewhere, this point will go over here somewhere. So let's just show those. So you can see this point has been reflected to this point over here. Now where this one will go, let's just show that on the diagram as well. Well, this point goes to this point over here. Okay. Now, if the length over here is 1 and 1 over here, hopefully you can see that the length over here is 1 and the length over here is also 1. Okay, now why did I want to do that? Well, hopefully here you can see that because we've reflected this point about this line, this angle is also theta. So here we have 2 theta. And I hope it doesn't take a lot of convincing to also figure out this angle over here will be 2 theta. Now why did I want to do this? Well, if we consider this point here, what we can do is form a right angled triangle, as we see over here, for this particular point here. We want to figure out the coordinates. Well, going across we have, you can see this is going to be in the x direction cos of 2 theta, and in the y direction we're going up by sine of 2 theta. Hopefully that becomes obvious from here. And if we consider this triangle over here, the coordinates of this triangle here, well, if we form a right angled triangle like so, then the coordinates here, well, we're going, if we consider this over here, we're going sine 2 theta across, and going down we've got minus cos 2 theta. Okay? So all this is very helpful, because what we can now do is consider our relevant mappings. If we consider our point over here 1, 0, let's just write it down over here. This point over here has been mapped onto this point in orange over here, which is cos 2 theta sine 2 theta. Okay? And what you can also see is that this point over here, the 0 across 1 up, this has been mapped onto this point in green over here, sine 2 theta minus cos 2 theta. So from this we can form a transformation matrix. For the first column we've got cos 2 theta sine 2 theta, and in terms of this column we have sine 2 theta minus cos 2 theta. So what does this represent over here? Well, it would represent a reflection in the line y equals tan theta x, and happily for us, in the formula book, that's shown over here. Number 7, we've got this matrix M. It has elements minus root 2 over 2, minus root 2 over 2, root 2 over 2, and minus root 2 over 2. And for part A we have to describe geometrically the rotation represented by M. Well, if we take a look at what we've just mentioned, clearly we've got a rotation and we need to figure out the angle. The angle is not so obvious for us. So if we take a look at what we have over here, we essentially match this up with what we have over here. Now over here, if we match everything up, we've got cos theta equaling minus root 2 over 2, minus sine theta equaling minus root 2 over 2, sine theta equaling root 2 over 2, and again cos theta equaling minus root 2 over 2. Now, of course, we've got a rotation, so this is completely fine. We also need to know what angle are we rotating about. Of course, we're going to be rotating anti-clockwise, that makes complete sense, but we need to find out that angle. Well, if on our calculator we do the inverse cos of minus root 2 over 2, you can see here we get 135 degrees for theta. And let's confirm whether this works for the sine as well. So if we do the sine, the inverse sine of root 2 over 2, we get 45 degrees. But does 135 degrees work if we type in the sine of 135 degrees? Do we get this value over here? Well, yes, we do. And if we do the minus sign of that, indeed, we get this value over here. So the angle that we're interested in, you can see clearly here, theta is equal to 135 degrees. So when we come to describe geometrically the rotation represented by m, first of all, cos of 135 is minus root 2 over 2, so that's correct. Sine of 135, that's root 2 over 2, so this is correct. We have m, which is a anti-clockwise rotation through 135 degrees about the origin. Now for part B, we have to describe, we have a square S with vertices 1, 0, 2, 0, 2, 1 and 1, 1, and we have to find the coordinates of the vertices of the image of S under the transformation described by M. So with each of these coordinates, we have to apply this transformation matrix to it. So we have our transformation matrix over here. Now what you can do just as a shortcut, if you've got all these coordinates here, instead of us writing this matrix out 4 times, which will take a very long time, we can write out the vertices of S as a matrix. So we've got 1, 0, that's this coordinate, 2, 0, 2, 1, 1, 1. So now if we multiply to get a final matrix, working all of this out, of course we've got a 2 by 2 times by a 2 by 4, the result will be a 2 by 4. So we've got here minus, if we go across and down, we've got minus root 2 over 2 plus 0. So here we've got minus root 2 over 2. Then here we go across and down, so we've got minus root 2 0, so we get minus root 2. Then here we've got minus root 2 minus 2 root 2, that will be minus 3 root 2 over 2. And finally we've got minus root 2 over 2 minus another root 2 over 2. You'd find this to be minus root 2. So this row over here tells us the x coordinates of the new shape S dash. And if we find out the corresponding y coordinates, well here we've got root 2 over 2 times 1 plus 0, so here we get root 2 over 2. And then if we go here, we got root 2 plus 0, so that will be positive root 2. Then here we've got root 2 minus root 2 over 2, so that will be minus root 2 over 2. And then here we've got root 2 over 2 minus root 2 over 2, that's just 0. So what you can therefore see is that the vertices of S dash we have over here, if we write all of these down, we've got minus root 2 over 2 and root 2 over 2. That's this coordinate. For the next one, we have minus root 2, root 2. For the next one, we've got 3 root 2 over 2 minus root 2 over 2. Okay, and then we've got, for the final one, minus root 2, 0. So these are the new coordinates of the image. Okay, so hopefully what I've said there made sense. Now you could just write this matrix times by basically this matrix, then this matrix times by this, then this matrix times by this, and then this matrix times by this. You could do it that way, but I think writing it down on a single matrix, all these coordinates here, just makes it, the working, a bit tidier. So that's example 7 done.